Okay, I think I have recording. Okay, guys. Here we have closed domain question answering system for medicine and clinical questions. Raquel, Ross, and myself, Maysam, under Dr. Slater, has done this research. The motivation for this research was because we wanted to get a specific question, a specific answer. That's what QA does, especially in closed domain, that can offer answers that internet can't. And machine language comprehension grows more capable. NLP techniques has been applied in this research. And what QA system is, it's technically text processing and with computational methods delivers the answer. And technically you have a passage, sentence, and questions and answer all in your data set. And that's how techniques can be applied to this data set to extract the answer from the text. And technically there is open domain and closed domain of the QA system. And technically the closed domain, the concern might be private document, or if you have certain data set, that's where you wanted to use closed domain. And for example, if you have certain research or your document is a specific, so you can use closed domain. And we have to use NLP techniques. Recently, it has shown a great and significant precise, specific answers for specific questions. We are using BERT, and my friend Ross going to start from here.
Right. So when we talk about NLP, there are several methods and models that are capable of NLP tasks. And these models gain language comprehension by calculating numerical representations of word meaning. NLP methods differ greatly in how they calculate word meanings. Our research project uses the BERT model, which is bidirectional encoder representations from transformers. What's special about the BERT model is that it captures word embeddings. It calculates word embeddings based on the context of every input text, which calculates context to a high level and helps the model understand language. The training phase of BERT consists of two tasks which help the BERT model learn word embeddings and sentence context. Basically, what the BERT model is good at is capturing context and using that context to better calculate outputs. The BERT architecture is as follows. After the context is calculated, the information flows to the decoder where outputs are generated based on the existing calculations. So BERT is primarily a language comprehension model. In order for the QA task, BERT requires the output layer to be fine-tuned to output answers. Now that the BERT model is trained, it can generate answer predictions by predicting the segment of a document where the answer begins and ends. Now Raquel will talk about the data set we used and some more of the methods.
Okay, thanks for us. So now that we cover about BERT, how are we using BERT to get our medical question answering system? So we use we use the BioASQ dataset. The BioASQ dataset is based on research paper. Now this is an example how it looks like. We have a question which is connect to a subset of research paper link, and then each of those one have an answer, and then also we have the concept too. This is how we define our search into three stages. The first stage is the retriever or the pre-processing. The second stage is the core or the BERT fine-tune, and the third stage is the reader. In the following step, we're going to go into those more details. So the retriever or pre-processing, what it's doing is taking the BioASQ set, and then since we have one question with multiple links, you're going to split those one into different questions per link, and then do the web scraping to get the context out of it. Now, the output of that is parsed into a different format that BERT will understand. Now that we have the BERT format input, we're going to pass that data into the BERT-based model. Now with the fine tuning, now what we're going to do, we're going to tune or train our few last layer of the model into the final BioASQ model. What the reader is doing, now that we have the BioASQ model BERT version, we're going to pass the question, and then it's going to give us an output. We have different approaches, and we saw some roadblock on the way, and then we overcome those ones. So this is what we have seen. We went from the F1 score of 10 to F1 score of 76, which is really great. Now, as you can see, we have one of the top 5 score today into the BioASQ challenges, having an F1 score of 76.4. We're very confident that our solution is working. Thank you for your time.